Another glorious day of calculus. Today we are talking about limits, and I know we did a whole chapter on limits, but when we did that chapter, all of our limits had x approaching a number, x approaching 3, x approaching -2, or whatever the case may be. Today is all about what happens if x is approaching infinity or x is approaching -infinity, basically for really large values of x or in the positive or negative direction. Now, the nice thing about this lesson is you already have a lot of familiarity with it because a large part of the lesson revolves around horizontal asymptote rules, which we'll get into in a second. So I have this right here, and if you think back to when we started limits, we started the process by making tables of values. And I want you to look at this table right here. I constructed this table with my graphing calculator, and you could write these values down if you choose. But I want you to look as x approaches infinity. So basically, as x is getting really, really big, look at what the y value is approaching. The y value is getting closer and closer to 2. And as x approaches -infinity, this way, the y value is also approaching 2. So the limit of this function, we'll call it f of x just for shorthand, as x goes to positive or negative infinity equals 2. So you can do your analysis by making a table, but if you think back to your horizontal asymptote rules that you talked about in Algebra 2 and that came up in pre-cal, remember if your degrees are the same, then your horizontal asymptote is whatever your leading coefficient is. So we didn't have to make a table, but I wanted to show you the table confirming that the y value is going to get closer and closer to 2. So we are going to be using a lot of horizontal asymptote rules when x is going to infinity or -infinity. I am going to scrap this little theorem here. That's not going to play a role, so don't worry about that. All right, so I have some examples here. Now, when I talk about horizontal asymptote rules, they only work if you're dealing with polynomial numerators and denominators. That's going to come up so what I mean by that is I can use horizontal asymptote rules on any of these three problems because there's polynomials on top and bottom. But if I look up back here, these are not polynomials, so we have to do some other analysis. These are trig functions, so we have to do some other analysis. We have an exponential function. So horizontal asymptote rules are only going to apply with polynomial stuff. The other stuff, I'll talk about here in a second. So if you remember limit properties, you have a couple options on this. You could get common denominators and combine these and then use horizontal asymptote rules. Or with limits, you can actually split it up. We talked about several limit properties back in the day. But we could split it up, and if you take the limit of any constant, regardless of what x is approaching, the limit always equals that constant. So we know that's 5. Now, if you look here, think about what happens as x gets really, really big. Like if I would plug in 100 billion, think about what's going to happen to this fraction. We would get 2 divided by some huge number. 2 divided by some gigantic number is getting close to 0. And so we could use horizontal asymptote rules. Remember, if the degree on bottom is bigger than the top, then your asymptote is 0. But I also like to think about what would happen if you plug in a really giant number. Well, this quotient is going to approach 0. So we would have 5 minus 0, and we get 5. So I look at the next one. I have the limit as x goes to infinity, 2x plus 3 over 3x minus 1. And I'm actually going to talk about two different ways to do this problem. Okay. The first way is, let's look at horizontal asymptote rules. Anytime you see x going to infinity or -infinity, the very first thing I would think about is, can I use my asymptote rules? And remember, if your degrees are the same, then it's just going to be whatever your leading coefficient is. So in this case, 2/3. So I already know the answer. But what's come up a few times in this class already is L'Hopital's rule. L'Hopital's rule. I've said we never really have an official lesson on it, but it just comes up, as we go through the course, through lessons, that by the end of the course, you'll have a really good understanding of this. But we can use L'Hopital's rule when we're doing limit problems anytime we have 0 over 0, or if we get infinity over infinity. most times this is going to be what's happening. But we can apply the rule if this happens. So I want you to look at what that means, how we could apply this using L'Hopital's rule. Say I would, now I'm going to use air quotes here, say I would plug in infinity. Now you're never really going to plug in infinity, but say I plugged in a giant positive number, okay? The top is getting really close to infinity. 2 times infinity plus 3 is infinity. 3 times infinity minus 1 is also infinity. This is a candidate for L'Hopital's rule. And the way L'Hopital's rule works is I would take the derivative of the top, then the derivative of the bottom, and then I would reapply it. So this is not something you have to do. I'm just using this as another way to show you how this rule works. So 2 on top, 3 on bottom, and then again, the limit of any constant is just that constant. So just a different way of getting the same answer. I always like to show multiple ways to have in your back pocket. The next one, the limit as x goes to infinity. Well, I'm going to use my asymptote rules. The degree on bottom is bigger than the top. What this really means is the bottom number is going to get gigantic compared to the top number. That's how I want you to think about this, because when we do get to these other types of problems where we can't use rules, we have to think in terms of domination. Like, which one dominates the other? I know that sounds, weird to say, but this bottom number is going to eventually dominate the top number. And so that's why if the bottom number is gigantic compared to the top, we get 0. But again, if your bottom degree is bigger than the top degree, your horizontal asymptote is 0. And then the last one is, let's say your top degree is bigger than your bottom degree. Well, that means that you're not approaching anything. The limit doesn't exist, right? Like there would be a slant asymptote if I would divide this out. But we're not even going to get into that. So the limit does not exist anytime the top degree is more than the bottom degree. So those are our asymptote rules. But now let's talk about some other weird scenarios, okay? So rational functions will always approach the same horizontal asymptote toward infinity or negative infinity. It's not always true with non-rational functions. So non-rational functions are like non-polynomial top or bottom. I used to teach this a lot differently than how I'm going to show you here. What I've learned is if these questions pop up, they are going to be multiple choice questions, and so your work doesn't have to be super clean. And you'll see what I mean, why that's important here in a second, okay? So if I look as x goes to infinity of this, now here's the thing with infinity or negative infinity. The only things that really matter are the leading terms. Like this plus 3 and this plus 1 here are really doing absolutely nothing as x goes to infinity. So I don't even need to worry about these. Here's what I mean by like this isn't proper math notation, but in terms of getting to the answer, that 3 and that 1 are doing nothing. Forget about them. And so now let's think about what we have here. On top, we have 4x. On bottom, the square root of x squared. Now, a lot of students might think the square root of x squared is x. And that's incorrect. That's a wrong assumption. And I want you to understand why that's wrong. I'll tell you what it is, but I want you to understand why this is not true. If you say this is true, then you are saying, if I took the square root of negative 3 squared, right? If I have x be negative 3, then your claim is that this equals negative 3. Like that's your claim if you're saying this rule is true. So this is not the true rule. The square root of x squared actually equals the absolute value of x. It's always going to be the positive of whatever this x value is. So if I come back over here and I take the square root of x squared, that's actually the absolute value of x. Now, let's think about what happens if I would plug in a really big positive number, right? Think about what happens to this fraction. For let's just start with 1,000, okay? If I plug 1,000 in for x, think about what happens. We would get 4,000 over 1,000, so that's 4. If we plug in 1 billion, we would get 4 billion over 1 billion, which is also 4. And so essentially you can see that this limit equals 4. Just by ignoring the stuff that doesn't matter and then applying the limit to the stuff that does matter, you could see it right here. But now let's look at what happens if x approaches negative infinity. So I'm going to do the same thing. The only things that matter are the leading terms. So the 3 and the 1 are doing absolutely nothing. So I'm going to take the limit as x goes to negative infinity. And I'm going to do the same thing I did on the previous one. On top, I have 4x. And then on bottom, the square root of x squared is the absolute value of x. Now think about what happens if I plug in a really big negative number. Let's say negative 1 million. Well, I would get negative 4 million on top. I would get positive 1 million on bottom. Negative 4 million divided by 1 million is negative 4. So now you're making the top negative and the bottom positive. You're getting negative 4 instead. So with rational functions like these ones over here, had I made this be negative infinity instead of infinity, the answer would still be 2/3. If I made this negative infinity instead of infinity, the answer would still be 0. So for these ones, it doesn't matter with infinity or negative infinity. When you get into radicals and non-rational functions, now you need to be a little more careful. And then we have trig. So the limit of sine of x as x goes to infinity. Well, for this one, let's think about what the graph of sine of x looks like. You know, after we did tables back in the first chapter, then we looked at graphs. So look at the graph of sine of x. If I graph it to something wavy like this. But basically, it's never approaching a certain number. It's always oscillating, so this limit is never getting close to a certain number as x goes to infinity. So we say does not exist. So we're not using horizontal asymptote rules, we're just doing some other analysis. The next one's interesting. So back in chapter 1, we had those problems where it was like you had to memorize a few rules. You had to know that this equaled 1, right? There's no way around it. But I don't want you to look at sine x over x and just think it equals 1. That's only true when x approaches 0. When x approaches infinity, we have something else to consider. So let's think about what happens to the top and the bottom as x goes to infinity, okay? Well, on top, the sign values can only ever go from -1 to 1, right? Like no matter what I plug in for x, think about this. No matter what I plug in for x, the biggest this value on top can ever be is 1, and the smallest this could ever be is -1. So this value is always somewhere between -1 and 1. Now think about what happens as x goes to infinity on bottom. On bottom, this is huge. So on top, we always have a number between -1 and 1, always. The bottom's getting bigger and bigger. So we have a really small number on top compared to a gigantic number on bottom that's approaching 0. So this is just where there's not much work to do, but it's just kind of thinking, you know, what would happen graphically? What would happen if I plugged in a giant number to all these things? There is some thinking involved. Okay. The last one. I see that I have a non-polynomial on bottom, so I can't use exponent rules. Okay. This is where domination comes into play. You know, infinity is a really big concept, right? Now think about what would happen if I would plug in like 2 for these x's. Obviously 2 is not a very big number, right? But if I would plug 2 in for these x's, 2 to the 50th is a really big number on top, and I get 4 on bottom. So at first glance, you think, okay, this might be infinity. Well, if I would plug in 100, I don't have my calculator, but if I would plug in 100, 100 to the 50th is a really big number, but 2 to the 100th is going to be gigantic compared to 100 to the 50th power. What I'm trying to say is, in the long run, exponential functions are always going to eventually dominate polynomial functions, always. Like, as x gets big enough, at some point, this function on bottom is going to take over drastically compared to the top. So eventually, this number on top is going to be relatively tiny compared to the bottom number. Notice I say relative. Like the top number is going to be huge, but relative to the bottom, it's going to be small. My point is exponential functions dominate polynomial functions. So this is going to be 0. If you have a really big number on bottom compared to the top, that equals 0. And that's true no matter how big I make this exponent. You know, if I made this 5 million, or whatever I wrote there, I don't even know what 5 million, it doesn't matter. Eventually, 2 to the x will take over this polynomial function. Infinity is that gigantic, okay? So I wanted to point that out. I guess another way you can look at that, I think L'Hopital's rule, this came up on an FRQ the other day. I wasn't going to talk about this, but I got time, so why not? So imagine I had x to the 50th over e to the x, okay, the exponential. And the reason I'm using e to the x, we talked about the derivative of e to the x is e to the x. So just bear with me for a second. So imagine I plug in infinity on top and bottom. Well, I'm going to get infinity on top, infinity on bottom. So L'Hopital's rule. So then I could do the limit as x goes to infinity of 50x to the 49th over e to the x. Take the derivative of the top and bottom using L'Hopital's rule. Well, if I plug in infinity, I'm going to get infinity on top and bottom again. So we can use L'Hopital's rule again. I could take the derivative of the top and bottom again. And what you'll notice is e to the x, no matter how many times I do this, e to the x is always going to stay e to the x. But on top, eventually, if I keep taking enough derivatives, this exponent is going to diminish to nothing, and I'm going to have a constant on top. It's going to be a really big constant, but I'm going to have a constant over e to the x, some number, I don't know what it is, over e to the x. And then if I would plug in infinity, well, this is going to be gigantic compared to this number that's on top, whatever it is. So just another way of looking at L'Hopital's rule. All right, that's our lesson on limits as x goes to infinity. Think about your horizontal asymptote rules, think about domination, and you'll be good to go. Peace out.